Okay. All right. Okay, so thanks again everybody for being here. We're still here. And so I'm gonna, the last time I was discussing how one can try to compare different models of minimalism by comparing the algebraic structures that they give rise to. And in particular, so making the comparison between Stiller's version of minimalism, which is being used a lot in and also computational settings, and this new version of minimalism that I've been talking about. And the point that I was trying to make, although I will not go into details into Stiller's formulation because that's not the main focus, and the algebraic structure gets more complicated, and that's exactly the point that if you have this phenomena. So the main difference is the fact that in the new formulation of minimalism, you try to completely decouple the generative process of merge from the externalization procedure. As I was describing it, it's like a two separate process. You first have this generative process of merging and the action of merging workspaces, and which has this very well structured algebraic formalism, in terms of the hop algebra structure on workspaces and the operation of merge that use the coproduct and the product of the hop algebra, and they use this grafting operation in the middle. And that's also very similar. So these of algebra is a well-known of algebra that plays an analogous role in other situations in theoretical physics and so on, exactly where you meet the same type of constructions. So it's like a very natural kind of, including the way you write the merge operations, has a very natural form. And what happens with the older version of minimalism is that you don't decouple these two operations. You don't decouple the generative process of merge from the externalization. So you start already with trees that are planar. You only work with trees. You don't work with workspaces, and you also have all the labeling already. The checking, the feature checking, the matching of labels, and that it's already built into how you do how you do the merge construction. And so because you're instead of decoupling these two things, you're trying to do all of them at the same time. The effect is that the algebra becomes significantly more complicated. So the kind of algebra structure that you encounter is now significantly more complicated than the one that I described. And the product is forced to be non-commutative because the trees are planar. It is forced to be of this much more complicated form, where you have to break a tree apart and plug it on another one, because you are not allowed to produce forests. You're not allowed to produce trees or only work with trees. And then the form of internal merge that, where you cut off one accessible term and move it back, is, if you want to describe it in terms of the coproduct with hop algebra, there's some complicated algebra that you have to do to see it's not directly the coproduct anymore. It's something that is related to it, like some complicated calculation. And moreover, the fact that you have to do the feature checking while you do the merge means that all these merge operations are only partially defined. They're only defined when labels match. And so you end up with domains that check this label matching. I'm kind of trying to use more or less the same notation in Stabler's paper for all these matching conditions. You have labels that basically come from the head of the trees that you attach in the tree. And these are strings of certain symbols that describe the syntactic features. I'm not going to go into details of how to do that, but I mean, these things have to have matching initial parts that, in order for you to be able to do the merge operation, and then this part drops, and the remaining label is something that depends on what is left. But one of the effects of this kind of example of how you see these things, when you look at papers that use the formalism, I'm not no, as I said, I don't want to describe these things in detail because it's not my main focus, but what I want to say is that, you know, this problem of checking features and checking domains, you know, you want to be able to iterate these merge operations, because you know, in the course of the derivation, you might have to do several of them. And when you start to do several of them, these domain checking problem compounds, and you get more and more, you know, complicated feature checking. And you can actually measure exactly how this complication grows, because you can check, you know, the growth of these conditions. You know, there's a, and I don't want to give too many details on this, but no, you can, there's a simple counting formula for, you know, planar binary rooted trees where where the internal vertices are labeled by some strings of characters or strings of symbols, and you can look among them, like when you do these matching conditions, you kind of have one entity that has some label that's fixed, and you're looking for something that has a matching label or a matching beginning of label. And so you can count how many possibilities you have of finding that. And again, there's a simple combinatorial formula that gives you, you know, where this condition of matching. And so in particular, it tells you, you know, how small is the dimension of what you're trying to find inside the dimension of all the possibilities of you know, of the trees that you have. And you can see that, you know, like with one iteration of merge, you find a certain size of what you need to find to do the label checking, which again, you know, has a simple formula. But you can see that when you start to iterate, you apply, and you want to do an internal merge like n times in the course of your derivation, you know, somewhere, you know, and this now is going to depend on some, you know, the dimension of what you're looking for in the middle of what you have is going to again depend on some combinatorial, you know, formula, which basically come out of a simple binomial theorem. But you know, the point is that these things, you know, the gap that you get between the dimension of everything that you have and the dimension of what you're looking for is sort of growing very rapidly to every iteration. So this is also, you know, there are other ways of, you know, analyzing computationally the implementation of minimalism. I mean, Bob and students have done some work on that. And it confirms, you know, in a you know, somewhat analogous way, this fact that this feature checking, because you force, you know, your merge to also take into account that at the same time as the generative process of merge, it increases your, you know, computational complexity of doing that. Yes.
Is the so am I right to understand that the point is that if you kind of hardwire feature checking into your, you know, definition of like the generative engine, that's going to create a lot of complications, as you know, we're seeing, and therefore what we need to do is to kind of leave the generative engine kind of do its thing and then kind of filter out stuff that otherwise would be
right. So the alternative, right? That's what I was describing before, is that you generate all you can, right? Just by this free generative process. And then, you know, there is, in the externalization, there is this like quotient map where it just kills off everything. So there is where you know, bring in some labeling algorithm that's going to tell you, okay, certain things, you know, will die because they will not have a compatible, a viable labeling argument, and others will survive. But you know, you cannot decouple these two mechanisms.
Yeah, divide and conquer. The same thing happens with GPSG. That's why GPSG is it's a mess.
Mhm.
From a computational point of view. Because they try to fold it.
It's interesting,
Together,
intuitively you think it should
separate
be
apart.
the other direction. Like intuitively you think first you generate the structure, then you have to have this mechanism that kind of looks inside and sees what constraints are or are not violated.
Yeah.
Intuitively, you would think that's more complicated than just building the right structure.
Typically, divide and conquer is a very good strategy because you can modularize the constraints in their proper places.
Yeah, exactly. This allows you to kind of deal with them as separate problems. Yeah.
What's the complexity of the whole new externalization process?
Sorry?
What's the complexity of the whole externalization process?
Are we pushing the complexity in the?
Yeah, that's right. So exactly. So in a sense here, your all the kind of computational, let's say, checking things is pushed into this externalization map. And so it's true, there are several things that are happening at the same time in the externalization part. One is this thing of choosing the planar structure of trees. And that is where all these language dependent properties like syntactic parameters and so on get involved. Okay? And then at the same time, you also need to do some checking about consistency in terms of, for example, there's you don't want things that don't carry a good syntactic head, like to have exocentric constructions, those things you cannot label. So there's a situation like that you don't want because of this type of thing. So there's a few things that are involved. The way I was describing externalization is this two-step process. You first can do this assignment of planar structures with this section of the projection done from planar to non-planar trees. And then you have another quotient map that exactly throws away things where labeling out relatives are.
There is a question on Zoom. David has a question.
Oh, yeah.
Hi. Is externalization something that happens once at the end of, with respect to the final workspace, or is it something that can, or with equal computational complexity, could be happening repeatedly and cyclically? I'm asking because, there seem to be places where the logic of feature checking follows a bottom to top derivational sort of plans. So, something that happens lower in the tree can, with respect to feature checking, can affect things higher in the tree, but not the other way around, which is sort of natural to a linguist's eye, if feature checking is part of the merge operation.
Yeah. So I understand. This is a very good question. So I hope to say a little bit more, starting with today. But so in one thing that this observation that I was making last time, that you don't have a morphism of magmas going from the non-planar to the planar trees, means that you can, so if you have merge that's happening before externalization, it's also not consistently happening after externalization. That you cannot have it both ways, just because of this simple algebraic fact that you don't have a morphism of magmas between this. And so in a sense, this means that that the generative process of merge is happening first and externalization is happening after. Of course, you are right that there is some kind of consistency checking that you need across substructures. And this is actually something most of what I'm going to talk about from today's lecture on is the type of mechanism that you can use to do this type of consistency checking after the merge has happened already. So yeah, I mean, it's a very good point, but I hope I'll be able to convince you that this can be done.
Okay, thank you. I'll wait.
Okay. And complain if it's not clear. I got to it. Okay.
Oh, I never complain.
Okay. So okay, let me just finish, very briefly this comparison with the old minimalism. The other, this thing that I just said of the growth of the complexity, you can also see it in an algebraic form, in the sense that, the other thing that you can say is, because I have all these partially defined operations now, because of these feature checking and matching of domains, how are these domains compatible or not with the algebraic structure itself? So I have this, product and co-product of the relevant of algebra for this case, but do these domains preserve in some way the algebraic structure? And that's again a place where you see that there is a problem with the old version of minimalism, because you only have some partial compatibility of these domain checking for feature checking with the operations. So you have, let me just through. to it quickly, but, you know, if the compatibility of this domain checking with the co-product operation requires some kind of modification, slight modification of things, but it's more or less okay, you know, that's good because that's the decomposition part, and so this is fine. But for example, the fact that you have plenarized the trees before applying merge is making your product structure very asymmetric, and so this domain checking, the compatibility with the product is giving you something that's compatible with product on one side, but not compatible with product on the other side. I mean, mathematically speaking, these things are called, you know, the difference between right ideals and left ideals, where you have an algebra that's not commutative. And you find that you're exactly in a situation where, you know, this has a nice algebraic structure on one side, but not on the other side, which is you know, much less nice than the situation that you have in the other. And so you end up with, you know, when you try to iterate, you know, the merge operation, you end up with these things, which I'm not gonna you know, give all the mathematical definitions. They're called right module co-algebras. It means exactly that you have this asymmetry with respect to the product, and these grow in size again with the application. So it is another way of seeing this growth in size of the computational, let's go, finding the matching conditions, just expressed algebraically instead of expressed as a combinatorial counting of dimensions. So there are all these issues that come up that force the algebra to become a lot more complicated than it is in the case of the free merge theory. And there's one last thing that is also an issue with this. So in the new version of minimalism that I discussed before, you know, the external and internal merge are particular cases of one operation. And they are particular cases that come up as the leading order term with respect to that, you know, grading that I described, so that the minimal search, but they are special cases of one single operation, which is kind of what you would like. And you would like to have like one notion of merge that gives rise to everything that you need to use. But in this setting, you cannot do that. So in this setting, internal and external merge have very different algebraic properties. They give rise to different structures, algebraic structures. So they simply cannot come from one single operation. And this is also something that's conceptually, you know, problematic in the sense that, you know, again, you have to justify why two merge operations with different algebraic properties have come up, right? It's kind of more difficult to come up with an explanation for that. Whereas, yeah.
So, sorry.
Yeah, no, whereas I mean, if you have like a single operation that takes care of everything, it's kind of it's easier to justify that that's the main thing that has happened that gives rise to this combinatorial structure of the syntax generation.
So it seems like if you have so in the old minimalism, I guess you could call it, the features were kind of driving everything. Here they're driving nothing, right? It's really just, you know, this idea of immersion, and the features are kind of decorated at the end, right? And then so that decoration, which produces effectively the same output, is in fact qualitatively different from assuming that there's these lexical features that are kind of pushing, like driving the merge operation in a sense, or driving what the qualitative outcome is. Is that a correct way to interpret this conclusion? That like assuming that the locus of computation is done by the lexical items themselves, or like the syntactic features on the lexical items?
Sorry,
So in the old minimalism, as you confirmed it, the idea is that the lexical features
right.
are driving almost everything, right? That merge is sort of dependent on these features, and the
Yeah.
feature tracking happens as you go, and right,
Yeah.
and that's complicated.
Yeah.
So now I suspect this is a, you know, quite a significant linguistic consequence, which is that the lexical features in new minimalism are doing nothing. They are assigned after the fact by the externalization process. So in fact, the example that you had yesterday was like John ate the apple or whatever.
Yeah.
It doesn't matter that it's John or the apple or whatever.
Yeah, no, of course, at this level, no, in the sense that, no, at this level, no, when I describe the magma of syntactic objects,
Yeah.
that's just all the abstract binary with the trees where we labels decorated with labels in this set of lexical items, but any labels in the set will be represented, right? So of course, there will be things that don't have on the line, don't have a reasonable parsing, right? Because you could have, for example, the same lexical item attached to every leaf.
Right.
Okay, there is this funny example that you can form an arbitrary long sentence in English consisting of the same word buffalo, right?
Right.
Okay, so leaving the buffaloes aside, every other example of that will not be a viable object in the end. So at the end of the story, that thing will have to disappear, right? But in this magma of syntactic object, you also have all of those things. Because it just generate them, right, starting with your set of identities. So you're right. I mean, at that level, when you just look at these abstract, syntactic objects, you can have all of these things. So I'm gonna in a moment, come on to actually study to see what you do. For example, when you want to say, okay, but I want things that, for example, have a well-defined syntactic head. And so then you start to actually discriminate between these different type of syntactic objects.
Super,
Yeah.
okay.
Okay. All right, so this is just all I wanted to say about comparison with the older version of minimalism. So let me come down to exactly where your question was leading. So you're all trying to spoil my punchlines. So here we are. So let me make this first as a comment. This actually Richard came, asked us this question while we were writing this paper. So we actually added these things because of that, but then it's relevant for what comes next. So, for example, the question that you asked us is, can you in this model, can you replace externalization by some other kind of linearization algorithm? And for example, he has this LCA, linear correspondent algorithm, which is a way of assigning a planar structure to trees. And basically, this depends. Okay, you can express it like in his paper. It's expressed in terms of C-command relations, but it really just depends on having a syntactic head. Because then you look at projections and you look at this. So let me phrase it in a way that's slightly different from the way that he phrased it, but it's equivalent. You can show that easily that it's equivalent. So let me define something that I'm going to call a head function. So a head function on the tree, so by tree now I mean a non-planar. So I just mean one of the syntactic objects, like planar binary root tree. So I'm going to define a head function as for a specific given tree as a function from all the non-leaf vertices of the tree. So root and everything, not everything that has something below them, right? And it's a function from this set of vertices to the set of leaves. So I give you a vertex and I have to tell you where that vertex goes to one of the leaves, okay? So the way I'm thinking of this is that if I give you a vertex, you can look at the trees the accessible term that's hanging below that vertex. And I'm looking at whether this has a head. If it has a head, that's singling out one of the leaves. And I'm mapping this vertex to that leaf. Okay. And but for now, it's just a function. It's just a function from this set of vertices to the set of leaves. And I want it to have one property, one key property. So it's the only thing that I require about this function is that if you have a syntactic object that's inside another one, so I pick one and I pick one below it somewhere. And if the leaf, the head, right, that I'm assigning to this one above is inside the one below. It's one of the leaf that's actually inside the other one. Then it has to be the same as the head of the lower one. Okay. So there's this consistency. If my head passes through another tree, then it has to be the head of the other tree. All right. And so an equivalent description of what this property that I'm stating this as a definition. This is my definition of what a head function is. And so first observation, this definition is equivalent to saying that such a function is an assignment. So you imagine you have your tree, like my folder mobile of the first lecture that's hanging there by the root. So below each vertex, I have two strands, two edges, and I just decide, that I'm going to color one of them white and one of them black. And I'm just saying that a head function with the definition that I just gave is the same as making one such choice. So I start at the root, I go down, every time I have two edges, I decide that I'm going to color one of them white and one of them black. And then I can say, if I am at a certain vertex, I follow all the black edges, and from that way down, and that's going to take me to some leaf. And if I do this, the property that I just stated is automatically satisfied. And so this is a head function. And in fact, every head function is obtained by this procedure, by one choice like this. Okay, and so in particular, you see immediately that there are two power of the number of known leaf vertices, choices of the possible head function on your tree. There are all the possible choices of this coloring. At each vertex that has something below, you have two choices, which of the two edges you color white. Okay, so this is a head function. Okay, so this maybe at first sight, doesn't look, look like it, but this definition of head function that I just gave is in fact the same as the notion of head that Noam had in his paper, their phrase structure. So this is the way that he characterized it there. It said, okay, if you have a tree that's just a cherry tree with two lexical items, then you say that this head function is either one or the other. Okay, and then you can do it inductively. So you say that you have this notion of the head is obtained from by looking at projection and restricting to the element. So you basically inductively whenever you put two things together with a new root by merge, then one of them projects, and then the head of the whole thing becomes the head of either one or the other, which inductively tells you how to go down. And it's very easy. We have like a small lemma in the paper that's very easy to show that this definition is the same as the definition that I just gave a moment ago. So it's another way of describing the same thing. And of course, I said that there are all of these choices of a head function. And in particular, another observation that's very simple is that if I give you one head function, again, let me think of it as assigning black and white colors to each pair of edges below each vertex. It's also the same as giving me a planar structure of the tree. Because now I can say, okay, how do I embed my tree in the plane? Put all the black edges on the left and all the white. At each point, at each pair, I have to choose how to put it in the plane, this way or that way. And so, okay, put all the black edges one side. And if that was my way to go to the tree, I get a head initial, embedding. If I get a final embedding. But so that's one way to say that these head functions are also determining an embedding. And this is exactly Keynes' construction. That's his linearization algorithm, just redescribed in this terms. Yeah.
I can see how that would explain head complement order, but I don't see how it would explain the order of a phrase in the adjunct or a specifier. Because specifier will actually be typically on the left. But
yeah, no, I agree. This is not necessarily the planarization that you actually want. That's this is not a description of the planar structure that you want to assign through externalization that would take care of this kind of thing. I'm just saying that this linearization algorithm that which I kind of described is simply determined by following the head. And this would give you, it would give you a planar structure. It's not gonna be the same planar structure that you would wanna get through externalization, because, for example, this would not be language dependent. For the externalization that you want would have to take into account also issues of, the parameters of different languages, and you will also have to take into account, the structure that you're saying, that, what the position should be with respect. So it's not the question is, can you, replace the externalization by something like this and still make by this choice of linearization and still get the same output or not? To get the same for, algebraic properties of another one. And so, but there is one more thing. So right now I'm just giving you this abstract definition of head function. But of course, for something to actually be the syntactic head, there's an additional requirement that you want. It's not an arbitrary choice of a head function in this sense, but it's one where you want to be able to define the choice of one of these head functions on the basis of the lexical items that you have assigned to the leaves. Okay. Because those would be the one that, determine what your head function looks like, right? If you have a noun phrase, or a verb phrase, so this depends on what labels you actually have, what lexical labels you actually have assigned to the leaves. Then this is exactly where, what you were saying comes in, that, now your choice of head function is not just abstractly decoupled from what your lexical items of the leaves are. You want it to be incorporating some information from what the lexical items of the leaves are.
So then that's assigned after, or I guess you can do it before, but it's assigned after, the entire, merge operation takes place.
That's right. So now all your syntactic objects are built. Okay. All your syntactic objects are already built. And now the question is, can I assign a head function to these syntactic objects on the basis, that takes into account which, lexical items I have attached to the leaves of that syntactic object. Okay. And so the point here becomes that you cannot do that in a way that, that will allow you to planarize all the syntactic objects. Because, for example, you will end up in the examples let's say you have the same lexical item attached to all the leaves, and or you just even more simply, you have two syntactic objects where the head, where you do have a head, but the head happens to be the same. Right now you want to put them together in an external do this merge operation of the magma, and now how do you assign the head to one or the other? So you can see that. So the punchline is simply that there is a domain on which a head function is defined, and so you have everything you do is now on, say that we'll have to use the presence of a head function will be defined on a certain domain inside the set of syntactic objects. This domain is not stable under the merge operation. The merge operation has already happened. Right, because of what I said, you could have two that each of them has a well-defined head, but when you put them together, you get an isocentric construction that doesn't have a head anymore. So, but the point is that you don't need to worry about this because all your merge operations have already happened. So you're just identifying a class of the object that you have created that do carry a consistent head function. Okay. All right. So, okay. This is one thing that I needed to say. So what I'm going towards now is getting to start discussing the interface between syntax and semantics. And so for this one, first thing that I needed to discuss is this thing about head, because that is part of what you need for semantic parsing. But then I wanna take for a moment a little step back and revisit for a moment this core computational structure of merge that in this new formulation of minimalism that I have been describing in the first two lectures. And I want to tell you about an interesting analogy. So I'm not going to promise, I'm not going to give you a physics lecture, but I want to tell you about an interesting analogy between this structure and something that's well known to theoretical physicists and mathematicians, or mathematicians who work with theoretical physicists. And I, the reason why I want to do this is because, there's what I want to say about, the interface between syntax and semantics has a complete analog in the physics setting that physicists have been studying for a very long time. And they have developed mathematical tools for doing exactly that. And so this tells you that maybe you can borrow those tools that exist exactly for the same purpose and applying them to this computational process of syntax. Okay. So let me start by revisiting again for a moment this computational structure of merge. So as I said, we start with this free non-associative commutative magma that generates the binary rooted trees. For the moment, let me forget about the lexical items at the leaves, because I'm just looking at this computational process that puts them together. And for now, they don't play a role what kind of lexical item I'm assigning at the leaves. So let me just leave the leaves unlabeled. Okay. So I just have this, I just put an X for the whatever label you eventually want to put there. And just leave it alone. Okay. So this means you just get this binary rooted trees known without any assignment of planar structure, and you have this operation that puts them together. So again, you do the same formal trick that I described when I discussed the orthogonal structure. You just form a vector space on these objects, which simply allows you to formally take sums of when you have multiple outcomes of an operation, you can just write them out as a sum, as a formal thing. Okay, nothing serious about this. Okay, so let me leave the mathematical node aside. It's not important, right? But one thing that I want to mention is that you can also organize these trees in a kind of order of growing complexity, which is a grading, which is given by, say, counting the simplest thing is just count the number of leaves. So you count like how many items you have in your sentence right there. So how long is your sentence? Yeah. So let me just say that, okay, this is like an index of how large my trees are, right? How complicated my trees are. Since they're binary trees, it doesn't matter. You can order them by number of leaves or by internal vertices, or because these things are related by a very simple relation. So there's no one determines the other completely. So let's just count the number of leaves, which is just the length of your sentence. Okay, so you can then form a kind of variable, right? Your unknown x. And your unknown variable x is a formal sum of one variable for each length L. Okay. So this is just a formal object. You just write it as your unknown, and you write an equation for this unknown variable. The equation is that x is equal to m of x with itself. So from the mathematical point of view, this is a fixed point equation because you have a transformation, which is this quadratic transformation that takes x to m of X with itself. And you wanna look at where X comes back to itself. So it's a solution. If I can give you an X, which is a solution to this equation, this is a fixed point of this merge operation. Okay. Okay, so what do these fixed points look like? Well, because this X has one piece, this variable, formal variable X has one piece for each degree, you can try to solve this equation inductively by degrees, by growing degrees. This is typically how one tries to do this, to solve this type of problems. You just try to find a recursion that solves it inductively. And so you can say, okay, if I do have a solution, this will also have one piece of the solution in each degree. So what does the piece of degree n looks like? So it's the piece of degree n of this merge. So it has to be, to get something of degree n, like when you merge, n is the number of leaves, right? So when you merge two trees, if the number of leaves is n, the number of leaves of one piece and the number of leaves of the other one have to add up to n. So you're summing over all the possibilities of decomposing n as the sum of j and n minus j. And so your solution of degree n solution is the sum of all the possibilities where there's this many, j of them go one side, n minus j go the other side. Okay. So, and then you can start from the beginning, that when you have only one, well, there's nothing to split out, it's just itself. So the first one is just that. But then two, you only have either one or one, and so you get just the one that has one and one on the side. But now when you look at three, you have like one and one, and so on. But because these are now not planar trees, they are abstract trees, that these two possibilities are the same because this n commutes, is commutative. So you have twice the same thing. And then you can feed this into the next step and so on. So you see that what you get as you get a sum of objects, a sum of planar trees, planar rooted trees, and you see that you generate all of them. So in degree L, you find a copy of each one of the abstract, binary rooted trees with L leaves, and they come with coefficients because you're doing this sum thing. And what are those coefficients? Well, those coefficients tell you how many different planarizations you have for that abstract tree. Yes.
So this isn't it's not quite a superposition of these trees on top of each other, is it? Because it's iterative, it's iterative, right? But if I were to think of the end stage of this generative process, it is something like a superposition of all the embeddings of a particular tree. Or sure.
Coming?
Yeah.
Am I allowed to make a
Sure.
side remark? So side remark, if you want a much earlier, but sort of in the same ballpark example of this, you could refer to the Chomsky-Schutzenberg J paper from 1963, Algebra of Context-Free Languages.
Right.
It's exactly this kind of construction, where it gives you all I think that's a good.
Yeah, it's a kind of recursive construction.
And when I think
I
about
agree.
like your example
That's-
of x and x,
It's a possible parsing.
right?
So that turns out to have this algebraic structure you can solve this way.
Yeah, so the main, so if you want, the main observation that I'm making here, is that this generative process that I described in terms of this magma can also be seen as the solution, the recursive solution of a single fixed point equation that you write formally in this way. You can encode your entire generative process into a single fixed point equation.
Right, and that's in that Chomsky and Schutzenberg, where they actually write equations instead of having a formal, that's their version of the quote, formal grammar.
But it's not quite a parse forest in a way, right? I represent like, it's two different parse tree analyses for the same quote tree, I mean, abstract tree in your sense. In a parse course, you get kind of an overlapping of the different.
Right, so here, it's not exactly like the parsing situation. It's a parsing situation, you're sort of mapping these to some, whatever, parsing, whatever, summarizing something. So I will come to that.
Okay.
But for now, I'm just looking at the generative structure itself and trying to do it
okay.
in this. So this is just encoding the same generative process of the free symmetric merge. But I'm just saying that it's the same thing to just describe it as the solutions of this fixed point equation. That's, yeah. And so the reason why I'm mentioning this, it's because this is if you want, the basic fundamental case of something that is called Dyson-Schwinger equation, combinatorial Dyson-Schwinger equations in physics. And they are all described in this way, so as formal fixed point equations, where you have some kind of polynomial functions. In our case, it's just a quadratic function, but it's like some polynomial function in a formal variable x that has several degrees. And this B operation that I'm writing there is exactly the one that I wrote when I defined the merge action on workspaces, that takes like a forest and hangs everything by the same root, which in the case of binary is exactly applying this M merge. But if you have a polynomial that's not quadratic, then you get these other grafting operations where you have more than two terms and you hang all of them by the same root. So these Dyson-Schwinger equations in physics are the recursive constructions of the solutions of equations of motion in quantum theory. So they are a way of combinatorially describe this least action principle of the question that in classical physics is just the least action principle of that equation of motion satisfied. So this way of describing this generative process of merge is sort of saying that it is like a fundamental, least action type of choice that is governed by the same structure that you find in fundamental physics. And you see the kind of objects, combinatorial objects themselves that you encounter in physics are slightly different from the binary rooted trees, depending on what this fixed point problem is. It also tells you what type of combinatorial objects you get as solutions. So if you want to make a comparison a little bit more flesh out a little bit more what the comparison is. So in physics, the combinatorial objects that you're dealing with, that your generative process produces for you, are the Feynman graphs. In linguistics, they are the syntactic objects. And here's an interesting point. You can say, if you compare like older description of generative processes in linguistics in terms of formal languages, you can do that, right? For example, this older version of minimalism, like Stabler, they do have a description in terms of multiple context tree grammars, so you can describe them in terms of formal languages. Of course, Bob showed that that's not efficient at the computational level to do that, but you can do that, and you can do that with Feynman graphs as well. You can write a formal language that produces the Feynman graphs of your favorite quantum field theory. Is an example. You can take the by physical theory, which is a form of quantum electrodynamics, and you can describe a generative grammar in terms of graph grammars that generates the Feynman graphs of that theory. So what I'm saying is that, however, this is not what physicists want to do. And the reason why it's not what they want to do, to use this formal languages description of this combinatorial object, is again because that's not an efficient thing to do. And well, first of all, in the quantum field theory setting, if you try to do that, you always land in a context sensitive case. So for example, all this parsing stuff that, for formal languages works well for context-free stuff, or at most for very mildly context-sensitive, like tree-adjoining grammar with concept sensitivity, just what we pick a word, that's right. But it's, when you go to actual context-sensitive stuff, it doesn't work. And so, it's, so physicists have, already long ago come up with this fact that there is a better way of describing this generative process of Feynman graphs, which is not formal languages, but it is of algebras. And in particular, okay, you can think of the generative process as, so you can do exactly what we've been discussing. So the generative process of the Feynman graph is described, in terms of something analogous to the magma of syntactic object, which is the solutions of these Dirichlet equations, and they form a Hopf algebra, like the word spaces, where exactly you take disjoint union as a product, and you take the coproduct that extracts substructure and takes the residual part of that substructure. So it's exactly the same setting that I've been describing. And this, it took a long time in physics to come up with this mathematical formulation. It was at the end, combination of physicists and mathematicians. It's called the Cohen-Kramer of algebra. There was, a lot of work done around that. This point about 15 years ago or so. And so the thing is that, you kind of recognize that this setting is exactly the same setting. And of course, this is one thing that I said at the beginning of my lectures, that the one thing that the mathematical formalism allows you to do is to recognize when the same fundamental structure occurs over and over again in different contexts, and recognize that when you meet something like that, it means that there's like a kind of universal law that you are describing that manifests itself differently in different contexts, but it's kind of the same thing at the end. Yes.
Yeah, so I mean, I'm convinced that, this is a very useful parallel, and that we should absolutely explore, this Hopf algebra structure as a way of thinking about, and these, dx equations as a way of looking at the interface and so on. But I guess, you said I'm not sure if it's an exact parallel, and I want to push back a little bit on the idea that it's exactly the same situation in physics as it is in linguistics. You had mentioned that, the problem comes when we encounter these, truly context-sensitive type patterns. But that if things are context-free, maybe it's okay, or if they're just mildly context-sensitive, it's also okay. But one of the things that, so I don't know if I'm convinced that the formal language approach is sort of, not going to be a still useful way to look at things. So I'm thinking in particular of something that, it seems like we have, like one way to get these mildly context-sensitive formalisms are these kind of mildly context-sensitive patterns in a fairly tractable computational way. Is you take a regular tree language, and then you can apply a regular you can subject to a regular tree transduction, and then the yields of those trees that you get at the end will give you these mildly context-sensitive formal languages, the types that we see in natural languages. We don't go beyond, into that truly context-sensitive area. So I guess on one, and then there's some suggestion that maybe that the regular tree languages that we care about, and the regular tree transductions that we would need under this view, aren't going to be just arbitrary, tree recognizers or tree transducers. They'll actually have some, particular properties that would help isolate some things out.
No, I understand what you're saying. And of course, also with this description of formal language description of Feynman diagrams, it depends on your physical theory. You could get some cases where it is just mildly context sensitive, depending on the theory. And then you could say, okay, I can still push this type of parsing that's works for context free and adapt it or something like this. So what I wanna say, is I'm trying to, so why physicists really think that this algebra approach is better in the end, even in cases where you could have something that's very mildly context sensitive or potentially context free.
Right.
And so let me come to that, because that's the starting point for you know, our idea of how to build, you know, the interface with semantics. So, you know, that, okay, this, in the final case, is examples of how you do this coproduct and algebra structures. And, you know, examples of how you build this recursive solution of Dyson-Schindler equations, you know, where these polynomial equations are slightly different from the one of linguistics, and they generate slightly different type of combinatorial objects, but this formalism is the same. But let me come to the point of where physicists really want to rely on this algebra structure. So, you know, in physics, you know, once you have your Feynman graphs, what would you want to do with them, right? So you want to assign some values to them, because, you know, what these Feynman graphs describe is some kind of physical events where certain, you know, fields interact, certain particles, you know, come together and form new particles and split off into other things. So they kind of represent some kind of physical event, and you want to associate to them something that you can compute that gives you the corresponding, you know, expectation value of that event, you know, some kind of, like, you know, whatever you want to compute, you know, the momentum that you can see, distribution that you can see, so, you know, whatever, you know, actual observable you're trying to evaluate associated to these physical events. Right? So, the key here is that you want to assign meaningful physical values to these combinatorial structures. This has been like one of the most difficult problems in the history of physics of the 20th century. We deal with how to do that, because when you try, you always run into things that don't make sense. Don't make sense because they generate no infinities that you don't know how to treat. You don't know what they mean. You don't know how to get rid of them. So everything goes up, everything diverges. So this is known as the problem of renormalization in quantum field theory, and has been like one of the big stumbling blocks in the development of modern theoretical physics. So the key to that question is how to extract a meaningful part of your calculation from these combinatorial objects in a way that is consistent over substructures. Because the thing is, you know, you get one of these Feynman graphs, and it contains smaller graphs. And because, you know, you go order by order in physics, when you do this perturbative quantum field theory, you go order by group number of your graphs, which is the measure of the size of the complexity of where you are in the construction of these graphs. It's also like this L variable, right, of the recursive equation of Dyson-Schindler. And so you want to solve this problem in an inductive way, so that you have solved it already for the smaller graphs. And when you encounter again a smaller graph inside the bigger one, the way that you want to solve the problem for the bigger one has to be compatible with the way you have already solved the problem for the smaller one. Okay. And so, yes.
Compatible means that if you have the solution for smaller parts, you can compute the solution for the bigger parts just on the basis of what you know for the smaller parts.
So it's not necessarily that you have what you have already determined for the smaller one will completely determine the bigger one. But what it means, it's kind of the other way. Like if you have a way of determining the bigger one, it has to be the case that what you restrict to the smaller one is compatible with what you have already found for the smaller one. Right? Yeah. So in a sense, I think you can see the analogy, right, with semantic parsing, because right? Suppose that you wanna assign some kind of, semantic parsing to your syntactic object. You have substructures. Okay? And each of them, about each of the substructures, you can also ask what is the semantic parsing. And now, you also have to have some compatibility, right? The way that I'm parsing the larger structure has to be compatible with the way that I'm parsing the smaller structure. A lot of these examples of ambiguities, right? Ambiguous parsing, they exactly come from some mismatch between, the assignments that you make to the substructures and the assignment that you make to the bigger structure, right? So it's you see that in a sense, I'm asking the same question. Okay. So this is like let's say the motivational starting point for how we want to think about this question. All right. So let's come to.
I just have a quick side comment, which is that I think what you said in the previous slide.
Yeah.
Is actually can be discussed in terms of, assigning values to structures. We want to do that in a compatible way with the substructures. But those values, so here you're going to think about in terms of semantics, getting kind of semantic meaning out of it. Also think of the interpretation as one where you're extracting some kind of linear structure. So you can use the same kind of, as far as I can tell, you can use the same kind of strategy here to also linearize these structures, because you're just getting a different kind of interpretation.
Yes, so I'm gonna come to that point, that of course, there's gonna be some kind of interaction between this externalization that I talked about that assign linear structures and this parsing semantics. And so, I'll come to discuss that. I want to also say that, back from this slide, that there is kind of an intermediate step between what the physicists have done and this proposal that we are making now about applying it to the syntax semantic interface. And just some time ago, a mathematician, Riemann, had adapted this renormalization story of physics to analyze into the theory of computation, so to analyze undecidable problems and trying to see if one can extract computable parts from non-computable functions. And again, it's sort of like a problem of infinities, right, where infinity in this case is like the fact that the halting problem is unsolvable. But you can see whether substructures actually carry computable and so on. So in a sense, there's like this intermediate step that tells you already that this formalism of physics applies to settings that are in fact closer to what one sees in music, but they deal again with a different kind of infinity, a different kind of assignment or extraction of meaningful values. But it sort of shows that this formalism has several possible applications that all have kind of the same flavor. Okay, so this is the premise or why we want to think about the syntax semantic interface and the way we do. Okay, so let's start. So then let's start to build something along these lines. And so to do that, I'm gonna start with some very basic kind of conceptual requirements. Of course, this is gonna be inevitably sort of controversial, but let me see. Let me just say why I want to make some requirements like this. So what I want to show is that even if you make the side of semantics as simple-minded and naive as possible, syntax is so structured and so has a very powerful computational structure, and it is enough to be able to give you ways to do some interesting syntax semantics interface, even when you have very little to go by on the side of semantics. Of course, if you're a semanticist, you say, wait a second. I mean, I want my semantics to be nicer. And I'm fine with that. I'm not objecting to having more structure on the side of semantics, but I just want to mention that you can capitalize on how much syntax is structured. And in such a way that even if, your model of semantics is very poor, you can still do something interesting. That's the plan. So let's kind of try to articulate this. So let's articulate this as some basic guiding principle. So I'm going to call the first one autonomy of syntax. And what I mean by this is that what I described, the generative process driven by merge of syntactic object, is independent of semantics. It just happens on its own. It's a kind of computational process that just happens. Okay, it just generates syntactic objects. And the second principle that I'm gonna discuss is that I'm gonna say syntax supports semantic interpretation. And basically what I want to say with this is that this view of the syntax semantic interface is a very syntax first approach. So your interface proceeds from syntax to semantics. Okay, so syntax is driving what is happening. And the third principle is that to some extent, I'm gonna, of course, this is exactly what we were saying moments ago, that is not completely, there's gonna be interaction between these things that I'm gonna discuss, but to some extent, the issue of semantic parsing and the issue of externalization can be treated as like two separate channels. Okay, and you can think of this as having this core merge computational system, which is a merge mechanism, and then it has two interfaces. One, say, with the conceptual intentional system, which is the syntax semantic interface, and one with the sensory motor system, which is the externalization. Okay, these two channels will have to talk to each other at some point. We'll see that they do, but a priori, you go these two ways. And the fourth principle that I discuss is compositionality. And what I mean by compositionality is exactly that you need a mechanism that takes into account consistency over substructures. Okay. So these are I'm just going to work with only these as my basic assumptions. And so this is the illustration that is in non-merge and some Liguistics book. So the first part, the thing, you have this word space, lexical items, syntactic object, word space with the action of merge. And then you have the one channel that goes down to externalization and the interaction with the sensory motor system. And you have one channel that goes to the syntax semantic interface. And system of thought, conceptual, intentional. So this is kind of what this same picture looks like in the setting that I'm talking about in these lectures. So you have this mechanism comes from the tree-symmetric merge. It produces these non-planar trees, which are the syntactic objects. And you have these workspaces of algebra and everything that I discussed in fact. Then you have one channel that goes to externalization, which is this consistent choice of planar embedding that is language dependent and takes into account syntactic parameters. You eliminate things that don't fit with various type of constraints. So that's one thing. And then the other side is you map something to semantic spaces. And here I put this drawing of something that looks like some word space where your tree now looks like it's embedded in this space. And that's what I'm going to talk about. And the thing is that these two things actually eventually combine into a single process. And I'm gonna be explaining what those pictures of these pentagons and other stuff look like there, what they're doing there. Okay, So it would be the nice geometric spaces that actually parameterize what is happening in these different channels. Okay. So now let me be even more, even more controversial in what I'm saying. So I'm in this construction that I'm gonna describe, the roles of syntax, so this interface, right, that I'm gonna describe, the roles of syntax and semantics are completely different in nature. Syntax is a computational process. In this description I'm gonna do, semantics is not a computational process. And the reason for making this choice is exactly that I want to keep the information on the side of semantics as unstructured as possible in order to point out what the role of syntax is. Okay. So, you can add structure on the side of semantics, but the minimal kind of, so I want to point out what is the minimal type of structure that you want to have. And the minimal type of structure you want to have is something that allows you to make comparison that are more like topological in nature, so some notion of proximity or similarity. Of course, this is going to be compatible with a lot of some of the models of semantics that people use, vector space and stuff like that, right? So my point is that even if you want to use one of these more naive models of semantics, you're going to get something out of it as long as you can have some way of describing some notion of proximity on the side of semantics. That's yes.
Proximity between what?
Yeah, so this can mean different things. I'll show various examples that where proximity is different. As you can manifest it in different form. But for example, you can say whether you have some kind of degree of agreement or disagreement between two points in your semantic space. Right? You can say whether how well they go together or don't go together. Are they close to each other? Are they far away from each other?
But the points are like meanings of sentences.
Yeah, the points, yeah, a priori is gonna be, well, to begin with, you will wanna have, points in your whatever your semantic space is gonna be. You wanna be able to map lexical items there. And then, yeah, you wanna be able to map syntactic objects, right? Or at least some subclass of syntactic objects. Maybe not all of them will have a good mapping.
Is there a specific reason to go for such an impoverished view of like the semantic space? I mean, the way we know that, I assume that, you can't do propositional logic on that view of semantics.
Right, so you're right that, okay,
So you won't say at least we can do that, right?
Yeah, so as I'm saying, I'm saying that even if you don't, assume, logic, for example, okay, you can do something like Boolean value, assignments, that's one possibility that we discussed. But in general, even if you don't assume like a propositional calculus or something, you can still get something. And you can still get something because of the fact that the computational structure of syntax allows you to do some comparison over substructures, and that already gives you some information. If you don't, bring in heavier tools on the side of semantics. Okay, so now this is. As I said, now we want to borrow some canons from physicists and use them, to address this setting. So here's the main way that physicists do this type of checking over substructures. So let's assume that I start by having some kind, so I have some kind of semantic space, and I'm going to be very vague about what I mean by that. Right? As I said, it's going to be some space where I'm going to have some kind of notion of agreement, disagreement, proximity, something like that. But I don't want to assume anything more about it for the moment. So S is this very vague semantic space, and I want to start with something that at least assigns for me some points in this semantic space to the lexical items. Okay, I mean, if you take one of these, vector space, like the semantics that people use in computational linguistics, then, you can say that, okay, you have a vector, right, that's attached to each of the lexical items, that the coordinates of that vector depend on occurrences of this word in some corpus, blah, blah. Okay, that's one choice, I'm not saying, so, I can, the point of what I'm saying is that I can be doing something pretty poor on the side of semantics, but it's, I will still be getting something. That's okay. So you have, something like this, and then, you wanna try to extend this to an assignment to more structured objects than just the lexical items. And you want to incorporate in the map, so you want to now construct the map, extend this map, so it's going to be what it is on the lexical item. You want to extend it to the more structured, syntactic object, consistently with what it is on the lexical items, but you want to do it in such a way that you incorporate in your function a recursive mechanism for checking consistency over substructures. The key of what the physicists do, and this is exactly where this hot algebra point of view is used. What the physicists do, they want to have the checking of consistency incorporated in the function that they're computing. So it becomes a recursively defined function that as you compute it, it checks for you that everything is consistent without you having to do two things separately, assigning the values and checking consistency. The assignment of values is already checking consistency. Okay. And so the physicists have a name for this recursive construction of consistency checking. They call it the Bogoliubov preparation. This is actually used in quantum theory for this extraction for solving this renormalization problem. There's some similarities, if you want, with things that people are more familiar with in linguistics, so some kind of true values assignment using trees, which is known in context tree setting. But the differences are what I said, that the checking of consistency of substructure is built directly into the evaluation map, into the map. And also there's no context-free hypothesis that is needed for this. Okay, so what do you need to do? First of all, what do you need for something like this to be possible? To construct a function like this with these properties. So this kind of recursive construction of consistency checking requires two things. So it requires a way of extracting substructures and checking values on the substructure and what remains, so that you can make some consistency checking, right? So you need a mechanism that extracts substructures and what remains of the substructure. We already know what that mechanism is. The coproduct of a Hopf algebra is exactly doing that for you, and that's why you want the Hopf algebra structure here, because it's doing the extracting of substructures for you. Okay. There's another thing that you want, which is in your target space where your evaluation or your assignment of semantic values is taking place. You want there to have a way to separate out or to filter, by some threshold or something, agreement or disagreement. So that you can say, like, when I check over substructures, it's okay, it's not okay. Well, there's consistency, there's no consistency. So you want to have a way in your target space to separate out consistency and non-consistency, or agreement and so something like that. Okay. So there's an interesting point here, which is that these two requirements that you have, these two things that you need, one of them is entirely on the side of syntax. The other one is entirely on the side of semantics. Okay. So that these constrain the two sides of your interface. you need one property on the side of syntax and you need another property, different one on the side of semantics. It's important that you are not requiring that your map from syntax to semantics preserve the same kind of structure. So you're not saying that if you have a co-product on the side of syntax, you want to have the same stuff on the side of semantics. You don't. You don't need it. You only need it once. You don't need it twice. So that's why I'm saying the computational stuff is all done for you by syntax. And the only thing you need on the side of semantics is this filtering out of agreement and disagreement. And then all the computation is done for you by syntax. That's why I'm saying this is a heavily syntax-driven model of the syntax semantic interface. It's entirely syntax-driven, if you want. Okay, so yeah.
Maybe I should wait to actually see how this works, but I have difficulty comparing this to what I'm used to in semantics, which actually, first of all, shares all the assumptions that you had at the beginning, in the sense that there is autonomy of syntax and semantic is a function from syntactic structures to something, like a lot of the compositionality, of course. And but I can't try to compare what you're trying to spell out with what I find familiar. I'm actually having difficulty, in a way, I'm having difficulty, like the only part that was unfamiliar to me was the the claim that, semantic objects form a topological space, and that's it. Short of the that's it part, I can't identify points of difference to see, like.
No, I mean, of course, what I'm saying is that, this is what you can do when you take the absolutely minimal, requirements on the side of semantics. What you're saying is that you can be compatible with these 4 properties that I listed at the beginning, also by assuming more on the side of semantics.
I'm not sure if that's more. So suppose suppose S, the set of semantic objects, is a set of functions. Some functions, I mean, they don't, and you map syntactic objects to functions. And the mapping has only 2 rules. So for, just, there are 2 rules that completely determine the mapping, assuming, of course, that you don't want to do pure lexicon. That's broadly like one standard version of semantics that I'm familiar with. And I don't see how it's particularly.
Okay, yeah, maybe we should try to see like.
Because
whether it fits or
I'm
not.
not trying to push for that, I'm just trying to see if there's a difference, I want to see that.
Yeah, okay,
difference.
let me get more into how this works, so that maybe we can compare it better with what you have in mind, what you're working with, okay. All right, so with this setting, I'm saying that these are the way that you're building your construction, and these are the two things. So as I said, the first one is the hot algebra structure. So that we already know. What is the second one? So what is this structure on the target space that allows you to do this filtering out or separating agreement and disagreement? This is also an algebraic structure. It's not the same. So this map is not a structure preserving map. That the coproduct is only on one side, and these other structures only on the other side. But these other structure goes under the name of Rota-Baxter algebra or Rota-Baxter structure. So let me, before I define what it is, let me just give a very simple minded example, to see what I mean by having to build something that checks over substructure. So let's just look at these sentences. Like if I say France is a republic, okay, there's no ambiguous, everything is okay with this semantic parsing. I think nobody objects. If I say France is hexagonal, we all understand what that means, right? And if I put these 2 things together and I say that France is a hexagonal republic, it sounds funny. Okay. Yeah, it sounds funny because there's some kind of mismatch between these 2, parsings of the thing. Because we think that a polygonal shape is not an attribute of a form of governance. So, okay. So let's look at the syntactic object that we are dealing with. It's this, tree with this one, I'm gonna write it with the bracket notation. And the hop algebra coproduct is gonna produce these terms where you extract, an accessible term and you look at the structure that remains. And when you start to look at these substructures and the structure that remains, you immediately see that there are two substructures that have this unambiguous parsing, which are respectively the Francis a Republic and Francis hexagonal, which are okay. But you also see other terms of the coproduct which extract the problematic term, extract this hexagonal republic, which is the one that doesn't have. So, this is saying that, okay, when you compare all these different terms, you have a list where you see which ones are okay, and you see which ones, where exactly the problem is located, where exactly the mismatch is located, okay? So you want to have this thing built into the function that assigns your parsing. That will allow you to, carry the information of what is consistent and what is not, and exactly where the inconsistencies are happening if there are some. All right, so now let me come to the algebraic structure that you use to do this. As I said, there's something that's called a Baxter algebra. This, is a case that takes a little thinking to get some intuition for what this structure is. So let me first, yeah.
I'm afraid
Oh,
the time is, sorry, I was.
Oh, I'm sorry, yeah, I'm sorry, I wasn't looking at that. Okay, so this.
Yeah, maybe this is actually a good natural point to stop.
Yeah, no, perfect. I just saw you. I just was watching, looking at the watch. So, let's stop here. And tomorrow I'm going to tell you what these things are and how you use it for doing what I just said, to incorporate this checking of substructures. Okay, thanks. Sorry for that.